quick start over. All right, so my name is Josh Day. I'm talking about financial modeling on large and streaming data sets. So a little bit about me is I have a PhD in statistics from NC State. And while I was there, my research area was streaming data algorithms or online algorithms, meaning you're updating your model or your statistic or whatever it is you're looking at with one observation at a time. And when I go full screen, my mouse disappears. So I'm going to stick with this view here. So I'll talk about what OnlineStats is, which is kind of the main Julia package that I made and contribute to. We'll talk about visualizing big data and then working with CSVs, JuliaDB, out of core processing, and then I'm going to leave some time for Q&A at the end here. So first, what is OnlineStats? So OnlineStats provides online updating. So the word online here has nothing to do with the internet, but it just means you're only looking at one observation at a time. So it provides online updating for a wide variety of statistics, models, and data visualizations, as we'll look into later. So it offers some parallel computing primitives that enable you to do kind of multiple ways of parallel computing. And it makes big and streaming data analysis relatively easy, just because since you're updating things online, the data set that you're working with doesn't need to fit in memory. So OnlineStats, the types in there perform basically two operations. And so the first one is fit. And so this fit operation takes the statistic. So here is a very simple one here, which is mean. And I'm updating it with a single value. I can also update it with multiple values. So the other operation in OnlineStats is merge. And so instead of fitting new observations to this thing, I can merge two different statistics together. So if I make a second statistic that's a mean, and I fit that with more values, I can merge those two things together. And it basically acts the same as if I had just fit all of that data serially, as opposed to well, more or less in parallel. So you can see that this is what is enabling kind of the parallel computing capabilities of OnlineStats, just because when you, so this example here in the bottom left, so if we fit three separate statistics and then merge them at the end, so that is equivalent to just taking one statistic and fitting all of the data at once. So I've been working on OnlineStats for quite a while now, and there's a lot of stuff in it. So some basic stuff from means, variances, covariance, a bunch of other ways to kind of estimate distributions, some statistics, so reservoir sampling and statistical bootstrap to come up with variance estimates in the online setting. A lot of statistical modeling capabilities like linear regression, and a bunch of other stuff, as well as group by operations and hyperlog log, which is the approximate count of distinct elements. That's for when you have absolutely huge numbers, as well as parametric distribution fitting. So if you want to fit a specific distribution to your data, like a beta or Cauchy or gamma, you can do that in the online setting as well. So the main example that I'm going to stick with today is visualizing big data, just because that's, well, obviously that's the best thing that you can kind of see that's going on. So plotting data is typically used throughout an analysis. First, you want to understand what your data is before you actually throw a model or something at it. And then afterwards, you want to be able to visualize the results. So the big question here is, how do I plot a data set that might not fit on my laptop? So I could rent some compute, I could do cloud computing, I could buy more RAM, but those aren't, well, necessarily possible solutions for me. If I'm working with sensitive data, I might need it to stay on my machine, or I also might not, have access rights to put more RAM into the machine that I'm working on. So the types in OnlineStats that do big data visualization are called partition and indexed partition. And so we are going to take a look at some examples of that right here. So the idea behind these two types is that you can plot any size data set. And the way it basically works is that it splits time series into approximately equal size buckets of data. And then in each one of these buckets, that bucket gets summarized with another online stat. So here I am creating a partition, and then a series is a way of joining two online stats together. And then the two I'm joining are the mean and the extrema, so the maximum and the minimum. And so here I am fitting this object with 100 million observations. It takes just less than a minute to run through all of these things, and then it plots it here below. So you can see we're not plotting every single data point, we're just plotting these summaries of things, which basically enable us to plot this at all. So if I were to try to plot 100 million observations on my machine, my computer would choke very quickly. So this is a way of plotting basically a coarse view of your data, but it enables you to plot anything at all, which is what makes it useful. And you can kind of increase the number of buckets or decrease the number of buckets that you're looking at. But here we can see the number of observations on the x-axis, and then we're basically looking at cross sections of the data. And so each vertical cross section shows the minimum and the maximum, as well as the mean as that line in the middle. So that is for plotting just kind of one time series by itself. But a lot of times we need to make bivariate comparisons and look at two things at a time. And for that, OnlineStats has index partition. And this is basically the same concept as up above, but we are now indexing the x-axis by another variable. So here I am just plotting a bunch of random normal pairs together, so we'd expect to get kind of the circular distribution. But now the x-axis, instead of the number of observations, it is now based off of some other variable. And so this allows us to plot things together. So I'm indexing it by a float. The statistic that I want to calculate is a k-hist, so it's a type of histogram in OnlineStats. I'm going to fit all these things together. It takes about a minute, and then I'm able to plot it. So again, this gives us a very coarse view of the data, but since it enables us to plot anything at all, that's kind of why this is useful for us. Okay, so a big part of working with, well, data in general and financial data is working with CSVs. Just for better or worse, CSV is a standard format, and it's just prevalent everywhere. It's not the most compact format, but it's standard. So the CSV package in Julia works really well with OnlineStats, even though the packages, they're not aware of each other, they don't depend on each other, or they don't have any mutual dependencies. So CSV provides iterators for CSV files, so you can iterate through the rows of a CSV file, and then OnlineStats is designed to work with generic iterators. So that's kind of the power of Julia, is that now we can combine these things together and things just kind of work, even though they don't know about each other. All right, so for this example, I'm looking at this huge stock market data set that Kaggle has hosted. It's not actually that huge, it's only 700 megabytes, so this very easily fits on my computer. But the data sets here are so open, high, low, close data for every stock or ETF traded in the US. And so we have, over 7,000 of these CSV files. And so every single stock has its own thing. So there's Apple, and I'm not sure what most of these other ones are. Okay, and so we can take a look at just the head of this file just to see what's in it. So we have the date, open, high, low, close, volume, and open it. So with OnlineStats and CSV, so again, since CSV works with iterators and OnlineStats works with iterators, I can calculate statistics, or in this case, a plot, without actually loading that CSV file, or I'm not loading it into a data frame or anything like that. So here I've just made a little utility function, and so the important piece here is that I'm iterating through the rows of this csv.file object. So I load this file, and then for each row, I go through here, and then since I'm using an index partition, and I want to get the maximum and minimum indexed by the date, I'm giving these the date and the low value, and the date and the high value. And we can run that function, and all right, so now we've looked through that Apple CSV and looked at, so this is the entire history of the And again, we're splitting all of the dates into a number of different buckets and then plotting the result. So in this case, we can see up here that I'm using about 500 buckets to split this data into, but I could do whatever I want for that. We can take a look at a few others here. So here's Microsoft. What are some other good ones? Netflix. I'll go back to Apple. All right, so one thing that's problematic with csv.file is that it loads the entire data set. So pretend for a moment that this CSV is too big for my computer to handle, or maybe it's just slightly too large and my computer is getting sluggish just because it's using up so much RAM. CSV provides a csv.rows struct that lets you lazily read from a CSV file. So the important thing here is that it has a very minimal memory footprint because you only basically need to be able to load a single row into memory at a time instead of the whole file. So the benefit of this minimal memory footprint, it comes at the cost of not doing any type inference. So all of the fields of the CSV file are essentially treated as a string. So internally, it's stored a little bit smarter than the strings are in Julia so that it's reusing memory. But it's basically treated as a string. So the only difference between the function up above and my new function here is that I now need to parse the fields that I want to use. So I want the date, so I'm parsing the date there, and then the low and the high values I'm parsing as a double precision float. And so again, I'm feeding that to this index partition and spitting it out. And all right, so now we can see that my function works exactly the same, but it's using a lot less memory, at least all at once, because I'm only loading a single row into memory at a time now. And just as a quick example, let's plot these two things together. And we can link the x-axes together, so we have Apple and Microsoft on the same time scale. And let's see, let's throw Apple and Netflix together. Yeah, so Netflix obviously hasn't been around as long as Apple. There we go. So again, these aren't huge data sets. So Apple only has 16,000 observations, which is pretty easy to plot in most settings. Although I have noticed that with Jupyter, when you start plotting around those numbers, Jupyter starts to get a little bit sluggish. That's the Jupyter notebook that I'm working in right now. So this enables us to plot a bunch more things that we otherwise might not be able to. Okay. All right, so next we're going to talk about, so before we were only looking at one CSV file. So what if we want to look at all these things together? And so that's what we're going to use JuliaDB for. So JuliaDB is able to distribute the chunks of your data and also index them. So basically, you can sort various columns and have an ordering of, you can have multiple index keys, which allows for more efficient queries later on. And it's a tabular data structure, much like data frames, except it offers distributed and indexed versions of that. So I also like JuliaDB for its syntax for selecting and filtering and mapping. There's also some really good stuff as far as map reduce operations goes. And then it also has OnlineStats integration. So a common use case for JuliaDB is loading many CSVs at once. And as I just mentioned, it has some powerful map reduce capabilities. And one really neat thing is that you can use an online stat as a reducer. So instead of reducing with some normal function, you can give it a statistic, and then it will calculate that statistic on that data. So let's take a look at loading all these files at once. So this path variable is just a string, and it goes to the directory where all of my CSV files are. And so if I provide the load table function in JuliaDB with that path, it's going to automatically load all of the files into one. So I'm taking all of these CSV files that are in this directory, and I'm joining them into one table. And then I also want to be able to make queries that show which stocked tick we're looking at. So I'm saying the file name call is going to be stock. So I can go ahead and load that. This takes a few seconds to run, so I won't run it again right now, but we've got almost 15 million observations with all of our data together here. So as I mentioned, we can pass an online stat as a reducer. So here, let's reduce. So that means we're going to pass the mean function to this table, which I've called T. And then I'm going to select the open and close. And then I'm going to map a function to open and close and basically get the difference. So here I'm taking this function, mapping it to the open and close. So I'm taking the difference between the open and close and taking the mean value. So I'm taking the mean difference of the difference between open and close for all of my observations. So this just takes a second to run. And it does so in a very memory efficient way because we're only looking at 2 observations at a time, hence the reducer. So another really neat thing in JuliaDB is group reduce. So it's like a group by statement, but is much more memory efficient. So typically with the group by, you have to allocate a bunch of temporary vectors in order to apply a function to each group. But since we're using a reducer, we're only looking again at 2 observations at a time. So we're doing basically a group by, but in a much more efficient way. And so I am first, so I'm calculating the mean of the open price for every single one of our stocks. And we can run that here. And then I am mapping this value function to the second row. When I do a group reduce, it gives me this actual mean object in there. But if I'm not actually interested in that object, I want to extract the value from those things to get this table below. Okay. Okay, so remember the plots that we made up above where we were looking at kind of one thing at a time. So now I'm going to try making basically all of these plots at once. And so I'm going to do a group reduce, but now I'm going to use an index partition, index by date, and I'm going to take the maximum and minimum value. I want it to be grouped by stock, and then I want to select the date and the closing price. So after running this through, and I think this takes about a minute to run, so I won't rerun it again, but I end up with a table called all plots, and then here I'm using the @manipulate macro from interact just to select some of these things and take a look. Oh, but maybe I will need to run this again. Well, I just ran this beforehand, but of course, running live code is always a risk, and it appears I've broken something here. Anyway, so the way interact works is that usually that when I click this button, it should be updating this plot with IBM right now and Google and then Netflix. And it did work right before this, but I guess we can skip that for now. Okay. So before we get to kind of out-of-core processing and kind of in the Q&A and everything else, so I just wanted to mention a couple of interesting time series analysis tools that I've found. So I'm particularly fond of this singular spectrum analysis. This is a way of taking a single time series, and so here we're going to take only a look at Apple, and we're going to select the closing price, and we're going to analyze it on a 90-day lag. So if there's any kind of seasonal trends within a 90-day period, singular spectrum analysis is going to pull out those trends. So this isn't the best example just because you wouldn't expect to see seasonal or too many seasonal trends inside of stock price. But so we can see the main part of Apple's stock price is the trend, and it looks like it did pick off some seasons inside of this thing. So OnlineStats also has a variety of of tools for time series stuff, just autocovariance and autocorrelation. So most online stats objects have a plotting recipe, so you can plot that object and see what it looks like. So here we're looking at the autocorrelation for 1 year, so 365-day period. And clearly stock prices are highly correlated, so we'd expect this thing to be highly autocorrelated. Okay. All right, so I was searching, I was searching hard for a good financial data example that was larger than the RAM that I have available. But unfortunately, the closest thing I could find was this New York City taxi data set. So it's over 9 gigabytes, but I only have 8 gigabytes of RAM on my computer. So even if it was 6 gigs, I'd probably have a trouble opening it. But so I'm going to try to run some analysis on this big data set that obviously doesn't even fit on my machine. So again, I don't want to rent cloud computing. I don't want to buy more RAM. I just want to be able to get it to run on my laptop. All right, so first, all right, so here is the path to my data set, and I'm going to sum up the file size for all of the files in this thing and get the gigs. So I guess I was a little bit off. So it's about 8.5 gigs. And again, I have 8 gigs of RAM on my machine. And let's take a look at just the head of one of these files. So we get, there's a vendor ID. There is the time for when the pickup happened, a time for when the drop-off happened, the passenger count, the trip distance, and all these other different fields related to taxi trips. So every single taxi trip in New York City in 2018, I have in 12 different CSV files. So there's a different file for every single month. So here is the data for January there that we're just looking at. All right, so since the data is big, I don't want to load it all at once. So I'm going to iterate through the rows of the CSV file. And I'm going to skip to the third line because the data starts on the third line. And here I'm going to create a partition with a count map. So count map is counting the number of unique elements. And I'm going to look at passenger counts. So since we have 365 days in our data set, I'm going to split the data into 365 buckets. And then in each bucket, I'm going to calculate this count map. And so that is going to be calculated for the passenger count. So I'm trying to get the number of rides with 0 passengers, 1 passenger, 2 passenger, and so on and so forth. So we can see this takes about 3.5 minutes to run through all of this. So first I'm iterating through the files, and then I'm iterating through the rows. So I could definitely speed this up by doing something in parallel, but this is just kind of the quick and dirty solution of doing everything serially, but at least I'm able to run some sort of analysis on this data set, even though it is larger than memory for me. And so we can see this bottom thing here is gray. So I guess that is 5 people. And I guess it didn't quite order these exactly how I expected. And there's clearly some kind of bad data in here. So there's no way that there were 192 passengers on a taxi ride. But you can kind of pick up some of the cyclical behavior of, I'm not sure which peaks are weekends or which are weekdays, but it looks like green is 2 passengers. So maybe 2 passengers are peaking during the weekends. I don't know. But so that's kind of the cool thing, is that we're able to run this at all, just because, again, it's larger than the memory on my machine. All right, so let's do something a little bit smarter. So let's calculate basically the same information. So I want to get the distribution of number of passengers grouped by the date. And so if I'm going to run this in parallel, I'm going to use the distributed features of Julia. So I'm going to add procs. That's automatically going to add as many processes as I have cores on my machine. And then I'm going to use the add everywhere macro to send this line of code to every single one of my processes. So every one of my processes, I want to have this data path, and I want to load the dates, online stats, and CSV packages. So I haven't changed a whole lot. The biggest thing you'll notice is that I've thrown @distributed in front of my main for loop. So I'm looping through the files and I'm throwing this @distributed. So I think I have 4 cores here. So these things are going to be working in parallel with 4 files at a time. So I'm going to take file for the files in that directory. I'm going to create a group by variable. So a group by in online stats is efficient, is more efficient than doing a group by in a data table. So this is, again, only looking at 1 observation at a time. And then I'm going to iterate through the rows of my CSV files. And so again, since this is inside of the @distributed macro, these are all happening concurrently on different processes, just they're working with different files at a time. And I'm going to take the date. So I'm going to take the pickup time, and then I'm also going to take the passenger count. And again, since I'm using CSV rows, I have to parse these things myself. But so this is essentially the same data as I've taken up here, but up here, this took me 3.5 minutes. Now that I've done basically some very easy work of making it distributed, it runs in 97 seconds, which is pretty neat. And I'm really hoping this @manipulate block will now work for us. Oh, no, it didn't. And of course, I broke it. Well, so the way this should have worked is that I would click along this line and you would see the different distribution for every single day. But of course, running code is a risk. What's that? I'm sorry, was there a question? Okay. Well, so I'm rerunning this again here, and maybe this will work out this time. Okay. Gotcha. So this is kind of the power of Julia, is being able to do something at all. And this is basically how I work in Julia, is you take a task that is difficult, like doing processing out of core. I'm able to do that, at all in 3.5 minutes. And then with basically just a little bit of effort, I'm able to get that down to 100 seconds or so. And I think there's still other ways that I could speed this up. So I'm not using the threads macro in Julia. So Julia has a multi-threading built in. I've not tried to read through all these files with threading. So I'm just using kind of the basic parts of parallel computing with the distributed package in Julia. All right, so I wanted to leave as much time as I could for Q&A. But so that is the gist of what I had ready to present. I still have a few other things if people are interested, but I'd like to open it up for questions.
Yeah, you can type in your questions in the chat, and Josh will pick it up one by one.
Yeah, so WebIO is broken, I reckon, for @manipulate. Yeah, so I've had a few issues with WebIO in Jupyter. But again, I just ran this notebook right before presenting. Oh, yes. So actually, the Jupyter notebook and the slides that I'm using, well, I can just open those up. Oops. So I have a GitHub repo called Talks. No. There we go, which I just updated, and here we go. So inside of, you'll see 2020 and streaming data webinar. So there I have, so the slides, which are Keynote, and then the actual notebook that I'm working with there. Well, as you're thinking of questions, I'll show one more thing that I threw together here. So TrueFX is a website and they have an API. So it's for Forex trading, so foreign exchange trades, which isn't completely my area, but they have this endpoint that allows you to take the data as a CSV. So let's just quickly glance at that. So I can repeatedly hit their endpoint and get kind of the current bid and ask results for these things. And you'll see like the bid points, 862. Every time I hit this, these numbers will be changing. So again, so say I want to plot an infinite number of these things, I'm just going to continually hit their endpoint, update that value into an index partition, and then plot that thing. And assuming they don't kick me off for just bombarding their endpoint. So here I am like hitting this thing. Oh, there we go. Oh, I guess I don't know what error that is. So maybe some of the results are coming in as nans and breaking things for me. But again, so here I'm processing just the maximum minimum of this stream of data coming through. I just kind of like this example because this is actual streaming in real-time data. Okay. Have I tried using streaming tick data for a similar analysis? Oh yeah, so as in this example, yeah, so here is from some streaming examples. So I'm assuming there's got to be an API out there somewhere for stock data that we could do the same thing for. Yeah, and kind of the unique thing here that I'm using is I'm using HTTP, the HTTP package to just get the results from this. And this is just a much more efficient way than downloading the CSV and updating it. Yeah, so the question is, how does mixing parallelism with online stats that decay, say, exponentially work? So that you'll probably end up breaking things. So online stats has different weighting mechanisms, and let's see if we can just, I'll just pop open the docs page there. So say you want to throw like an exponential weight onto a mean. So an exponentially weighted mean works similarly to a moving window of a mean, but it's basically just a way that you're setting how you rate the influence of a new observation. And so OnlineStats has a bunch of features for different weight functions. And so the standard one is equal weight, and that's basically how you would get the equivalent offline result to the online version. But then there's also things like exponential weight, which is a constant, and a couple other weighting types that are designed to rate new observations as more influence. Yeah, so this will be problematic with the parallelism. So when you merge things together that have different decay rates, yeah, I provide no guarantees on what's going to happen with that. Question, can you provide an example or two regarding the current research being done with big time plus time series analysis? Once I'm familiar with factor application of vector autoregressive model. So unfortunately, that wasn't completely my area, was time series stuff. So my main research was in stochastic approximation algorithms. And that's for problems like, so as an example, logistic regression is something that you cannot do equivalently online as you can with the offline version. So stochastic approximation is the question of what's the best we can do given that we have to approximate a solution. So there is a lot of interesting stuff going on in the stochastic approximation fields. But so when it comes to kind of like online time series analysis, I'm less familiar with. So question, so I want to find out if it's possible to display progress when running a task in parallel. So I'm not entirely sure if the @progress macro is smart enough to work on the @distributed macro. Yeah, so I don't know if you can combine the progress and @distributed. I also don't even know if it's thread safe either. with the @threads macro. How about multidimensional data, i.e. time series, say a 2-dimensional array in this option chain? Yeah, so as in you want to track 2 time series at a time? Yeah, so let's take a look at that. So where is our JuliaDB example? Okay, the message is that show progress works fine with parallel loops and pmap also. That is pretty cool. So I guess my data set isn't in a great format for analyzing things together. So instead of looking at 2 different things together, let's look at a cove matrix. Okay. That's right, I had an infinite loop going on before. All right, so let's selecting everything here. So now I'm gonna, well, here I'm just calculating the covariance matrix between, well, every single open and high value across all stocks, which really I wouldn't want to do this across all stocks, but we're doing it anyways. And so we can get at least the covariance between these 2 things. Oh, and we can plot it and take a look at the, I think that gives me, no. Well, so there's the covariance matrix. Can we use the fast shapelet algorithm? So that I am unfamiliar with. Imagine a Rubik's Cube, i.e. 2-dimensional grid that grows as time progresses. 2-dimensional grid. So I'm not sure if I completely followed you. But so here's an example of working with basically a time series of multiple values. Just making sure I didn't miss anyone here. Oh, there's a question for a book on stochastic approximation. So to be honest, I never found a great resource. And I would avoid Wikipedia on it. So there is, someone out there does have some interactive tutorials on, so the main algorithms are like SGD and, let's see, SGD. There we go. So here is this is a good link, if this is the one that I'm thinking of here. And yes, yeah, this is it. Let's see if I can. Let's see. Any tricks around sorting over operations within group by and JuliaDB? Missing how you do that from a cursory look. Tricks around sorting. So what do you mean by over operations? So if you're talking about indexing a column, so for instance, my first column is already sorted, but you can set, so the P key is the primary key, and we can set these, well, I think we could set these to 1 and 2. So we want to get this data table sorted first by stock and then by date, which it already is, but when we tell Julia, or tell JuliaDB that it's sorted by these 2 things, it can make some queries more efficient, and it should print out with these names in bold to let you know that those are the columns that you're indexing by. Operations that rely on ordering of observations within a grouping. Yeah, so here is basically this is a quick way of making group by operations faster with JuliaDB. So here I've set the primary keys to 1 and 2. So now JuliaDB now knows that stock is ordered and then secondarily sorted by date here. And so we can actually do some group by stuff, and we should see that it's faster when you're grouping by stock on the index table here as opposed to the non-indexed one up here. Yeah, and you can see the only difference between the printout is that stock and date are now in bold, just to let you know that they're indexed. Yeah, so when it's kind of hard to show off, but really the group reduce functionality in JuliaDB is super powerful. Just because you can also map arbitrary functions. So here, so I'm going to select open. I'm going to map it to this function, which I'm just adding 1 to all these things. So it doesn't actually do anything. But it does this. Oh. So this isn't super useful exactly as an operation, but this lets me map kind of arbitrary functions to the data that I'm interested in before I throw the reducer at it, which is the mean. So this is what enables you to do map reduce. No, so what is JuliaDB is the question. Is it a database solution like SQL or MongoDB equivalent by Julia? So it's neither. I think it's a little bit misnamed. And really what it is, it's data frames with indexing and being able to distribute the data set. There is some out-of-core processing abilities inside of JuliaDB, but I've had some mixed results with that. Although I just saw on Discourse the other day, someone is, are OnlineStats and JuliaDB the same? No, so OnlineStats is my package that's only for the online calculation of statistics. JuliaDB just has nice OnlineStats integration so that you can throw an OnlineStats statistic as a reducer, which just makes it a lot more powerful as far as the kinds of statistics you can calculate. So any one of these things you could write yourself as a MapReduce, but it's a whole lot easier just to throw in, say, a variance object in here rather than figure out the math for doing it yourself. But I just saw on Discourse the other day, someone was working on a database in pure Julia that looked really interesting. Beware of any functions for online anomaly detection using OnlineStats. So not directly. So OnlineStats has a few ways of fitting distributions. So you could do some very simple anomaly detection, basically just by detecting outliers from just looking at like histograms and things like that. Yeah, so there's some parametric and semi-parametric methods of fitting distributions to data. So you could go take it a step further from that and use those to identify whether something is an outlier or not. But that's about the fanciest it gets for anomaly detection. So the question here is OnlineStats and JuliaDB have application only in time series applications, or can it be used in other, say, computer vision? Yeah, so that's actually one pretty cool thing about JuliaDB as opposed to, say, like pandas in Python, is that you can store any data type in it. Just because it's JuliaDB is 100% Julia, so any data type that you throw at it, JuliaDB can store, as opposed to pandas, which only supports a certain number of data types. So if you wanted to store, say, an image in the data table or whatever else that you want, or if you wanted to add units to a number inside of JuliaDB, that all just kind of works out of the box, just because it's Julia all the way down. Is there functionality in OnlineStats to account for time offsets, delays between variables? In the sense, so is that question in the sense of that you might not have like a regular time series, you might have observations showing up within like different cadences or at different time intervals? So if that is the question, indexed partition to cadences. Yeah, so if you're trying to compare two things, that is a little bit difficult. So I've actually been putting some thought into how I would incorporate things specific for time series in OnlineStats that deal with things like that. There's no kind of out-of-the-box solution right now, though. Maybe in a week or two if I figure out a good solution for it. So I just sent my email to the chat. If you have any questions that you didn't get asked, or if you just want to know more, send me a message and I'll get back to you. Well, thanks everyone. I'll stay on here for a couple more minutes just in case anyone has any last minute questions. But thanks again for joining. To get started, what is a good financial time series data set? So I do like this Kagel's huge stock market data set, just because it's a regular time series, so they're all by date, but then it also has kind of enough difficulty in that you have to join multiple CSV files together. So can you share a reference in a real life application, as in usage of JuliaDB or OnlineStats? So I know Domo, well, uses, they either use OnlineStats or a fork of it or some stuff that they've taken out of it. But that's my only knowledge of real life applications of it. Is it possible to handle data sets summing up to 100 gigabytes in an hour? I'm sure that would be just fine, just because I was able to run through 8 gigs in, well, my unoptimized code went through 8 gigs in 4 minutes, so that should be just fine. Good question. So what about using online stats with GPUs? That's not something that I've explored, even though I think that is a really good application. Right. So GPUs are doing or are good at doing lots of small operations, whereas online stats is kind of doing exactly that. So while I haven't looked into it, that's definitely probably a good source of speed gains. I also really wanted to get an example using the @threads macro at the bottom here, but I ran out of time.
I prefer going through this. I don't understand. People are online. You didn't mute it. We were.
Any more questions that you may have for Josh? You can type it in. Okay, I think, yeah, we have no more questions, Josh. Probably we can end the webinar here today.
Okay.
And in case any one of you have any questions, you can always write into me at sanjeev@juliacomputing.com, and I shall get back to you.
All right. Well, thanks everyone for joining.
Thank you.
Mhm.